Laid back. Laid back.
So now we can consider the case where C is not equal to 0. So C is not equal to 0, and we're never going to have C less than 0, because that would imply that the damping force increases your speed. So we have the case where C is greater than 0. So we have a positive damping constant. There are 3 cases. So before we go into the 3 cases, we will look at the characteristic equation, or characteristic polynomial for this equation. That's going to be lambda squared plus 2c lambda plus omega naught squared equals 0. Using the quadratic equation, we get 2 solutions. We get negative c minus the square root of c squared minus omega squared. And we get lambda 2 equals negative c plus c squared minus omega squared square root. So case 1 is what we call the underdamped case. So that's when we get distinct complex roots, or c is greater than omega naught. So this square root is has a positive number on the inside. So yeah, this leads to 2 distinct, or sorry, it's negative on the inside. The square root has a negative on the inside, so we get an imaginary or a complex solution. So 2 distinct complex roots, and the solution looks like this: y of t equals e to the negative ct times c1 cosine, actually I'll use the same notation, a cosine omega t plus b sine omega t. So omega is the new frequency of this of these oscillations, and it's going to equal the square root of omega naught squared minus c squared. And the amplitude is going to equal, the amplitude of this wave is going to equal what the original amplitude was. So what it would have been if there wasn't damping times this e to the negative ct. And the phase angle would still be b over a. So now we have second case, which we call overdamped. And overdamped is when C is greater than, this is supposed to be less than right here. So this is when C is greater than omega naught. And in this case we have a positive under the square root, so we get distinct real roots. So our solution is going to look like this: yt equals c1, or actually I'll use a e to the lambda 1t plus b e to the lambda 2t. And our final case is called critically damped. And that's when C equals omega naught. So we get one real repeated root in this case lambda will equal negative c, so yt is going to equal c1, or I'll just use a as our constant, a e to the negative ct plus b t e to the negative ct. So the way these solutions look graphically are do simple harmonic motion. Simple harmonic motion is just a regular periodic wave constant amplitude. Our case of our underdamped case will look like this. We'll be oscillating, but our oscillations will decrease over time. And they follow this exponential curve. The amplitude does. That approaches 0. Our overdamped case will it'll start off here and go straight to 0 asymptotically. And our critically damped case will go to 0, but it'll go to 0 quicker than the first case, than the second case, the overdamped case. And that's it for harmonic motion.